All right, so our next presenter is Mario Munich. He's actually a Senior Vice President of Technology at iRobot. I actually own one of those. Those are cool. And anyway, he's a PhD from Caltech and working on novel human-machine interfaces using object recognition, navigation, mapping, et cetera. And so he's going to talk about the challenges and the benefits of introducing a vision-based navigating robot and using computer vision. So welcome, Mario.
Thank you. Thank you. So I'm going to guide you through the journey to get the Roomba 980 with computer vision in a consumer robotics. So this is a marketing video that shows how the Roomba works. That's the challenge. Our spec was for 1,500 square feet. Now you have kids, you have toys, you have a whole bunch of things. And what you want to do is the robot autonomously go through the house, creates a map of the house, and cover every single place that is reachable with the robot. So this is how it's going through different rooms. And you can see the map on this side, and you can see the robot going back and forth in a systematic manner. And then at some point in time, it creates visual landmarks that you can actually recognize later on. And there is a point in time in which the robot starts getting out of battery. It's going to go to recharge and come back. This phase of the cleaning is when it is cleaning next to obstacles. As you see, initially it was covering the open space. That is the easy space to clean, and then cleans where there are obstacles, where a lot of the dirt is. It goes, recharge, and finish the whole room. You see there are no walls that are left untouched, and then that's done. So this robot had very simple sensors: odometry, a gyro and accelerometer, a mouse sensor, a camera, a bumper, that is the main touch sensor, that are two switches. That is actually quite coarse sensor to avoid going out, and it has a connection to Wi-Fi. So what are the challenges that we need to overcome to create this robot? The first challenge, or before that, Jeff told me that this was an embedded vision conference, and I need to explain why we're using vision. I'm a guy that came from the computer vision community, so to me it's obvious, but I'm going to mention it anyway. So the camera is a very cheap sensor that provides a lot of information. You can use the camera for localization and mapping, for like we do in this robot, object recognition. We can do semantic understanding. We can do user interaction, pet detection, obstacle avoidance, and many other tasks that are going to be powered with the AI algorithms. There are alternatives. Some alternatives are based on lasers. And these lasers give you either less information or they're too expensive. Once we started this work, the state of the art at that time was SLAM with lasers that cost $6,000. So that was a little bit too steep for us. So we decided to take the SLAM problem. This is a typical slide from a SLAM problem in which the robot is moving around the space, looking at landmarks, whatever the landmarks are, and estimating the position of the robot and the position of the landmarks. And this is based on odometry. And then this is what we wanted to do. Look at the environment from a low vantage point, collect information, and create our landmarks, or places where we see enough information that we can recognize later on. This is a typical pipeline. You have the scale space, you have feature detection, you start descriptors, You have a database that you can recognize. You estimate pose. You have creation of landmarks, and then you get the landmarks and the pose of the robot. This pipeline is very well known nowadays in the computer vision community. We started this work in 2002, and that was not that well known. Especially being able to encounter features in the database and do it fast, it was a challenge. Our first experiment was done in a household of one of our colleagues, and we ran the robot in the yellow trace, and if you only use odometry, you get the green trace that is diverging, and with the creation of landmarks and using BSLAM, we were able to stay on the trace that is the red trace. These blue dots are the landmarks, are the collection of features that you collect as you are traversing the space. One key element that you can see is that you don't have too many landmarks. So the system is going to be efficient in how you store information about the environment. So the accuracy at that time was 15 centimeters in position, 3 degrees in heading. It was robust to dynamic environment, and it was able to do kidnapping recovery. Kidnapping means the Roomba, the bin is full, you go, you want to empty it, and you bring it back. So the Roomba figures out what it is or what it was when it was left. So these are the people that work on it. But the problem was that BSLAM ran on a PC at that time, so you couldn't put it on a consumer robotics. So what is the other challenge that we have? And this is a big challenge that is many times overseen when you are looking at the product. Let's say that we want to have intelligent navigation in consumer robotics. And we are using consumer robotics, so the guidelines comes from the consumer electronics environment. So the rule of thumb of consumer electronics, anybody that works in the space will tell you that if you have retail price, your production cost needs to be between 20 and 30% of your retail price. What does it mean? Suppose that you have a $300 product that you're trying to sell. You only have between $60 and $90 to play with. This is your budget to get everything. Motors, wheels, buttons, plastic, CPU, memory, batteries, only $60. All of this for $60. That was something that I learned very early on, and it was a big realization that if you don't consider cost when you're dealing with consumers, it's very difficult to sell anything to anybody. Another way of saying it is that we as consumers are really cheap. So we need to have a solution that was actually efficient in cost. Not only was able to provide localization, that was state of the art, it was need to be efficient in cost. So when you are trying to go to a selection of the components that you're going to use, looking at the processor, well, do I perform my operations in integers, or do I perform it with floating point? Floating point processors have more area, they're more expensive, but they allow me to do optimization. What is the image sensor interface? Is it parallel? Is it MIPI? What do I have? What is the clock rate of the processor? Clock rate equates to cost. On the imaging sensor, what is the image size? Do I use a 5 megapixel? Do I use VGA, quarter VGA? More pixels mean more computation, so you need to have a beefier processor. That means that, well, you're paying more. What is the field of view of the camera? If you look at the cell phones, the field of view is about 50 degrees. But you look at the very small area. When you're trying to localize, if you have a wider field of view, it would be easier for you to know where you are. And this is a challenge because you cannot piggyback on lenses that are in the cell phone environment. You need to get your own lens, or build your own camera. And then RAM. RAM cost, and whoever is in the cell phone environment knows that the prices of RAM and LPDDR and so on and so forth are humongous. And more RAM tells me that I can cover houses that are bigger, but you're going to pay for it. So what is the trade-off that you need to make? So we have early on, and this was in a paper that published in 2010, we have a system with an ARM9 from NXP that have a vector floating point working at 266 megahertz. And these are numbers that were very reasonable. So we had selected a processor, we have selected a camera, it was a VGA camera, and this was all fitting, so great. We feel really good. We can do a demo. If you see here, we have an early Roomba. This was from a previous company before iRobot, where we slap our system on top. We can run VSLAM. We can go on a trip, and it will come back. It will figure out what it is. So we are really happy. But the only problem is that this is not a robot that cleans my house. So, OK, we are not there yet. So what I need to do is, now that I know where I am, I need to figure out how to clean in an efficient manner. Make sure that I take the information from the sensor, the information of where I am, and perform a systematic coverage system. So we had another paper, and we like to publish our work besides implementing it into actual products. And that was another big realization. If you have a technology, to get to a product that actually uses the technology, there is a big jump. You actually need to integrate it and make, trying to clean up the technology. Because usually when you have a technology, you do it in a demo, it works in some environments, but it doesn't work in any environment. And a robot, unfortunately, you send it to the wild, and you don't know what it's going to encounter. So, great. We have a demo. It can do mapping. It can do all the things that we wanted. Now we need to build the product. So usually what many companies do is, OK, you have a wall. Here is us doing product development, advanced development, and research, and product development. And now we throw this over the wall, where there is the other guys that are in the factory, wherever the factory is, and they put it there, and they have the Roomba. Well, actually, it is a problem, because this doesn't work either. You have a camera here, and this is a pictorial way of showing it, that you want to calibrate, because you want to make measurements. And calibration is not something that you go to any big CM that will know how to do it. So unfortunately, many times, this doesn't work. And what you need to do is also join the manufacturing. And it's an actually great process. And you learn a lot, because you learn what not to do when you develop algorithms and systems, because you can never manufacture. And these are systems that need to be built in the millions. And you don't want to get customer service calls. You want to get no calls. They need to be reliable in every single environment in the whole world. So we finally got there through all the challenges that I am outlining. And we have a robot that is being sold in huge quantities. And I'm going to make a plug for my talk tomorrow on business. So this robot has the possibility of mapping the house. And It would be able to collect information about the different devices, the IoT devices that are in the house, and enabling them to perform more intelligently, and more for that tomorrow. But we are not done. Computer vision has the beauty and the curse of being something that is really difficult and has many challenges for us. So this is the house of one of my one of my coworkers, and you can look at images from the same place in the kitchen, and these are all the degrees, the type of images that you get from exactly the same window. Depending on the time of day, it will look very different. These are from the dining room and from the foyer. And just to highlight, this wall of windows, if there is light, things will look this way. There is no light, it will look this way. So it's completely the opposite brightness pattern. And these are the lights. Lights off and light on. If you're using any environment, any technique that uses features, the feature that hook on this device or this brightness pattern will not work here. So that's a challenge. How do you do it? And this is one of the things that we are working on, and there are more environments. And the next challenge is that we would like to look at the environment. This is a typical household environment. And what we want to do is get this representation so that it is possible for the robot to understand where the objects in the environment are, clean better, clean more intelligently, and also enable another interaction between the robot and the user. Imagine that you can tell the robot, now that we have speech recognition, go and clean under the table. The robot needs to understand what the table is, how to get there, and localize it, and enable a pattern of cleaning in that environment. So that's the end of the talk. I hope that I have guided you through the journey, and I'm here for some questions.
So if you want to ask questions, please come to the microphone here, because it's being recorded. So. Any questions? Yeah.
So I have a question about vacuuming. Mm-hmm. When I'm vacuuming, I vacuum the entire floor. So why would you need to find the difference between a chair and a stool or under the table?
Yes, that's a very good question. The challenge is not with the vacuuming. The challenge is with the robot. The robot is the mobility of the robot is much easier when you go in open area, when you don't have obstacles, and you can understand where you are, you can look at landmarks, you can recognize the landmark. When you are next to a wall or against a chair where you have a small passageway that you need to go around, it's a lot more difficult, the maneuvering. So that's where we would like to know what is the environment so we can change the mode of operation of the robot. There is also the case in which you have carpet versus hard floor. When you have, and there are in the regular vacuum cleaners, you can change the setting depending on the type of surface. So in hard floor, you like to do one pass. Maybe if you have carpet, to clean it really deeply, you want to have several passes. So understanding the environment is very important. The other thing that provides us the understanding of the environment, and this is where cameras can help us, is that you know what is the bedroom, and maybe if you are connected to the internet, you know what is the time of day. And if you go further, you can understand whether people are there or not. Well, you like to be gentle with the user and not clean when it is sleeping or in the middle of the night or when the user is working there. So that will give the robot more autonomy and provide the user with a better device that will be more amenable to his uses.
Yeah.
Hi, very interesting presentation. I have two questions. I'm interested to know what processor manages all of the information to keep the robot on track. And my second question is, what trips the robot up? What is your greatest challenge that he runs into in failure?
Yes. So the processor that is managing all the information is the processor that is connected to the camera. It's the ARM9 from NXP at 260 megahertz. It's just to picture yourself, it's a processor of the flip phones pre-iPhone. So that's the computation that we have. What TRIP does is that since we need to make things cheap, we don't have a lot of sensors to detect cables and socks and rags or stuff like that, so we can get entangled. That's the main thing that impedes us from completing the mission, completing the run.
I like that you refer to vacuuming as completing a mission.
That comes from, so iRobot used to have its roots in the military. That's why they call it mission.
Oh, that's right. Okay. So the question I had was, I see these photographs and I think, gee, I don't want to be vacuuming in the buff with an iRobot. What's your security? You're putting this to the cloud. I'm terrified that Nielsen data or somebody's going to somehow snag this.
Sure.
And, yeah.
And that's a really, really important topic for us. I actually designed with another colleague of mine the hardware architecture so that in this robot it's virtually impossible to break it. To hack it, you need to be physically next to the robot and plug a JTAG and change the code. And by the time that you're there, well, you are in the house and there is no security anymore. But this was a challenge that or a way that we ensure that no images from users could get in the web. What we offer to people is, upon they decide to join, we can provide them a map of where the robot went so that they can understand whether it cleaned the whole house or not. But this is optional. And in the future, since we all know, we like it or not, cameras are going to be in our phones, are in our houses doing surveillance, and are going to be in more robots. We are using state-of-the-art security technologies, and we have very clear guidelines of no images anywhere in the cloud, unless the robot is for security. That's where you need the images there. But.
Thank you, nice talk. My question is opposite to the previous one. We are really fascinated by collecting huge amount of data set. You have any plan to enroll people to give you images from the houses of, and there is a business model over there? I can get a free iRobot if I give you some images from my home?
We can consider that. We need to talk with the business and the legal teams. We are actually, to overcome this challenge, because believe me, we are as paranoid as anybody about security, and we don't want to have a Roomba that is a mobile camera in your house hacked. We are paying companies that go to households and they collect the images for us. So they can do object recognition and we can start doing learning on these images. So there are no user information. It's something that is paid for. It's data collection. And we'll start with that and we'll see. There is one critical thing is that if you look at the camera is here. It's a completely different point of view of all the data sets that you see in the world. All the data sets are taken from this point of view. That is the user point of view. They're looking from here. So the possibility of doing transfer learning and so on and so forth is a little bit reduced.
So I'd been watching a lot of digital forensics, a documentary on it. What do you perceive, since you're not putting images to the cloud, is there any kind of storage? Could you think of a scenario where police would come in, say, the housewife was murdered, we know the iRobot, Roomba knows who did it. Is that even possible? I mean, maybe they can narrow down, it was scheduled to go at 1 p.m. and we know
I
she
can
died at
tell you,
12.
I can tell you, and you can make your own judgment. This robot has 16 megabytes of RAM. I think that answers the question. But anyway, for next generation robot with more RAM, I think that we are not collecting the images, we are collecting the feature that we extract from the images. So it would be difficult to do forensics, unless you have a robot for security. That's the purpose.
So I have a question for you. So I have one of the, like I say, I have one of the older models which doesn't have the vision on it. And sometimes it'll sort of get lost, you know, and can't find the charging station anymore. So now with the mapping, you're saying basically it will remember where it started from effectively and then be able to get back there when it knows it's running low on battery. Is that right?
Yes.
Awesome.
So you saw it in the video.
Yeah.
They stopped at the same time, went to charge, and since he knew what it was aware of the map, it could go back and restart the mission.
Very good. Any other questions? Thank you very much. That was great. Yes.